The next paper is a joint effort between Strasbourg and Caen in France by Metz, Saussey, Lavelle, and Kurudu, and I'm sorry for butchering all those names. The title of the talk is Study of Adsorbed Hydrocarbons during the Catalytic Selective Hydrogenation using in situ infrared spectroscopy.
So, the work that I present here is a collaboration between two laboratories in France. Philippe Metz and myself have initiated this work by investigating about the mechanism of butane hydrogenation on the metal catalyst. And the results that I will present you led us to investigate further about hydrocarbon deposit which occur during this reaction. And that was made by using infrared spectroscopy, and this work was made in the lab of Professor Saussey and Lavelle in Caen, in France also. But Strasbourg is located in the east part of France, and Caen is located in the west part of France. So, we have studied the selective hydrogenation of butane on platinum catalyst. The scheme of this reaction can be written like that. You can have two consecutive hydrogenation, one to give the olefin and the other to give the saturated product. But you can have also some direct hydrogenation to give the saturated product. And the challenge of this reaction is to enhance the proportion of olefin in the total product of the reaction. And we always study about the factor which govern this selectivity. So the selectivity is defined as a ratio between olefin and the total product. We have studied the platinum catalyst instead of palladium. Palladium is known as it's well known to be the best catalyst for this reaction. But in our experimental condition, palladium is so active that it's difficult to change the experimental parameter of the reaction and to study this reaction well. So we have preferred to study platinum catalyst. The reactions are made in a flow apparatus working at atmospheric pressure, and the partial pressure of hydrocarbon is 14 torr. And so we did this reaction first in microfilm, and in the other part I will show you in the infrared cell. So, in microfilm, I represent here the calorimeter signal, which is registered after the reactor. And you will, the catalyst is keeping under hydrogen flow, or hydrogen plus inert gas, it depends. But you will see that just after introducing the hydrocarbon pressure, because the signal gives a hydrocarbon pressure, you can observe some inward curve on this signal. And at the end, when you after stopping the hydrocarbon flow, you observe this desorption peak here. And if you do that in the same condition on the support, you don't observe these two phenomena. So these phenomena occur on the metal phase of the catalyst. And if you look about the conversion during this pulse of reaction and the selectivity, the conversion is in green and selectivity is blue line. At the beginning of the reaction, you observe a decrease of the conversion and an increase of the selectivity. and after you obtain constant condition, selectivity is high. And when you stop this hydrocarbon flow and you look about what contains this peak, it's only C4 hydrocarbon, butane, butane, butene, and mainly butane, I mean saturated product. Here you have no selectivity at all, but here you have again the high selectivity. So we call initial phase, stationary phase, and final phase. This initial phase, when you have this phenomena, can be longer. I will speak about this initial phase and final phase. I will show you the necessary presence of this hydrocarbon deposit to get a selective catalyst. After that, I will show you that this hydrocarbon deposit is very reversibly adsorbed, and we shall see after by inference too. First, the necessary presence of this hydrocarbon deposit to get a selective catalyst. For example, if initially you get a very high conversion, it means that you have chose your experimental condition and you have a very high activity. You never observe this adsorption phase, you don't observe the selective catalyst, and you have no this desorption peak. I will show you that here. For example, here you have this adsorption and desorption phenomena, and in this case you obtain this selective catalyst, which is this blue line up here. But if another experiment, I have doubled the, I have divided by 2 the hydrocarbon flow, it means that the contact time is higher, so I have a higher activity. And in this condition, I don't obtain this initial phase and final phase on the signal accelerometer. Now, I will show you how it works with the reversibility of this phenomenon. So, if you do a reaction, and if you obtain this, you chose your experimental condition, you obtain this adsorption phase here. So in this condition, you have a very high selectivity, here the blue line, and you have a conversion, which is here 60%, but it doesn't matter. And after that, you are here in the stationary phase. After that, you decrease your hydrocarbon flow. It means that you have a longer contact time, so you increase your conversion, and the selectivity is always very high. And if you continue this type of experiment, so you decrease again your flow, at this time you can observe a desorption peak of this signal. And during this time, you see the selectivity decrease, and the conversion is 100%. And you have the selectivity which decreases very much. And you can repeat this experiment by, you took again the first flow and you observe this adsorption peak, and the selectivity increase again, conversion is at the same level as at the beginning, and all that, you can do that, and at this time you obtain also the second desorption peak. And if here you stop your hydrocarbon flow, here you don't obtain the desorption peak that you have seen before, because it is desorbed here. So you can see that this phenomena is very reversible, and it governs the selectivity, because you obtain the high selectivity only when you have this hydrocarbon deposit on your catalyst. So now we did this experiment in an infrared cell, working in a dynamic condition and which is connecting with the gas chromatography. And I put here the results that we have obtained. After that, I will show you the spectra. During the initial phase that we have obtained, exactly the same. It means that the conversion decrease and selectivity increase. We have seen the appearance of a band at 1,687 minus 1 centimeter. And in the final phase, after stopping the hydrocarbon flow, we have observed the disappearance of this band. So we think that the initial phase and the final phase are well correlated with this FDR studies. And on the other hand, we will see that for two catalysts, one give a high selectivity, the other give no good selectivity. You will see that the coverage of the surface is very different. So that is the spectra, different spectra we have obtained during the initial phase. During the initial phase, it means that here you will see you have the conversion decrease, the selectivity increase, and after that it was stable. Conversion was stable, selectivity also, and also the coverage of the surface, it doesn't change at all. And if I want to explain a little this spectrum, it's a full spectra. Here you have the OH band, here is the CH acetylenic band, here is the methyl and methylene symmetric and asymmetric revulsion band. Here you have the CC triple band, and here you have the deformation of methyl and methylene group. So you can see here we have obtained this type of species which is adsorbed on the support, because the OH of silica move to the lower energy. Here you can see OH here, and you can see this vibration here, and also the acetylenic vibration here. And these three bands are characteristic of the absorption on the support. And you will see that this band increase during this initial phase. And you will see here the appearance of this band here. And this band occurs only when you have a high selectivity here. Yes. This band we have attributed it to état de butane because it's situated between the CC triple bond and the CC double bond. So, relating with the literature, we have attributed this band to this species here, which can be seen as a opened triple bond, which is adsorbed on the catalyst. And here is the final phase after stopping the hydrocarbon flow. You see instantaneously the disappearance of the species which is adsorbed on the support. We see here, and the CC triple bond disappear. And you will see that this band also disappear in here is the time, in 3 minutes. After 3 minutes, this band disappears also. So we think that the appearance of this band here and disappearance correlate well the adsorption and desorption peaks that we have seen in a micropilot reaction. I wanted to show you also something here. You can see that at the end of your reaction, a lot of band remain here, and that is a polymerization on the surface. And that is two examples that I want to show you. We have two catalysts. One was working and giving selective catalyst with 30% of conversion, and this one with the same conversion we don't observe a good selectivity. And in this condition you can see the difference between the coverage of the surface. The butane on the support is a very small quantity, and you have not the appearance of this band here compared to this one. So this result shows that when you have a high selectivity, your catalyst has to be saturated by butane, and you have also the appearance of this band, which we have attributed to an eta2 species. So all these results show that this hydrocarbon deposit, which govern the selectivity, is reversibly adsorbed. We can express that by this simplified scheme, and that shows that you have some equilibrium between this hydrocarbon deposit and the reactant. And if in the initial phase you have the transformation rate here is too high, you don't form this hydrocarbon deposit. That was the case. And now, if you choose your experimental condition to form this hydrocarbon deposit, and after that, if you change some parameter, for example, when you stop the gas phase, hydrocarbon flow, this species decrease. The concentration of the species on the surface decrease, and the equilibrium shift toward the right. And here you have a free site now for adsorption of hydrogen or butene, and you auto-accelerate your reaction, and you have this desorption in butane. And the same thing occurs when you are at the high conversion. You have a limit of the conversion, and if you are up to this limit, this is too small, the concentration of that is too small, and your equilibrium shifts to the right, and you have also this auto-acceleration of the reaction, and your selectivity is lost. We put also this route here for the formation of polymer, because we have seen that we have a polymer on the surface, and we have calculated the amount of this product, and we can see the variation of the amount of this product change with the parameter of the reaction, and we have correlated that with the formation of polymer. Now, I want to conclude, and only I want to insist of one result that we have obtained. If you can remind it, only this result is sufficient after so many lectures. Hydrocarbon deposit lead to the formation of selective catalysts by comparison to non-selective catalysts. And in the other end, our infrared spectra shows that the nature of the catalytic site is totally different between a selective and a non-selective catalyst. That is the main result that I want that you know.
Paper is open for discussion now.
There were suggestions in the literature that the hydrogenation takes place by the participation of the adsorbed hydrocarbons as hydrogen transfer agents. What is your opinion about this?
I think that selective hydrogenation, you have selective site and non-selective site. That is two different sites. And the selective site takes place where you have this hydrocarbon deposit. And I think that not as Sommerfeld proposed, the selective hydrogenation occurs on the metal, not on the hydrocarbon on the top layer. But it shows that some hydrogen can come from the hydrocarbon deposit. Because when we have done the deuterium tracer studies, we have no, hydrogen balance in our product. So we have more hydrogen that we have put on the surface. So it means that we have in our product, reaction product. It means that some hydrogen from the hydrocarbon deposit are needed in this reaction, because it seems that on the selective part of your catalyst, you have no equilibrium between H2 and D2 in the gas phase. But on the part of the catalyst where you have a non-selective catalyst, where you have not this hydrocarbon deposit, you have this equilibrium H2D2. So here you don't need a hydrocarbon deposit, is not necessary.
Thank you, I agree.
I probably did not understand the TCD experiment. As you know, the TCD signal depends also on the contact time with the TCD filaments. So if you increase the flow rate, you are decreasing the contact time, then you are decreasing your baseline.
You are decreasing your...
The baseline, because you are decreasing whatever is the flow rate if you have...
No. We are always constant pressure. We don't decrease which baseline? The baseline of what?
The way the TCD works, it's a Weston bridge, and the signal depends on the contact time of the molecule X with the filaments. So in your experiment, you are putting your molecule through the catalyst, and you are trying to increase and decrease the flow rate to decrease or increase the contact time with the catalyst.
Yes.
Your conversion selective, that's fine. But I mean, comparing it with the TCD signal that does not translate the catalytic behavior, it translates only analytical measurements. You see, you have increased in your TCD signal when you are increasing your contact time.
No.
And this is due to the
No, it's not true. It's not true. We can increase with contact time without changing the TCD signal.
You can increase the contact time of what?
Of hydrocarbon with a catalyst. When changing the TCD signal? No.
That's how TCD works.
No, it's not. We have two calorimeters, one before the reactor and one after the reactor. And we can see the difference between the two, and we have no influence on with the contact time on this signal. We have two calorimeters, one before and one after. And we can see which happened on the catalyst, because and which is not due to the change of...
So you can change your...
Perhaps you...
Do you have any information by which you can estimate the number of active sites or nature of active sites in these two types?
How to see? No, I cannot. Because we have tried to estimate the hydrocarbon deposit, but it's very high. It's nearly one butane for one site. If we compare with the dispersion of platinum, it's nearly something like that we have found. So, no, I think that we cannot estimate.
I noticed that you had a loss in the isolated Silenol group a broad band lower down came in the spectrum, and you attributed that to weak absorption of the butane on the cyanamide groups. But then after you had desorbed that material, I noticed that although the broad band had largely decreased, there was still quite a negative band in the spectrum due to the isolated SiOH groups. And I wondered whether some of the residual hydrocarbon bands that you see in the spectrum may be attributed to the buildup of hydrocarbon on the surface of the silica, converting OH groups on the surface into some sorts of alkoxy groups, maybe ethoxy groups.
It shows that we have a polymerization. We have polymerization on this catalyst, and is the reason why. So I don't know where I located this polymer, but maybe it's a frontier between silica and metal. Because if we did this experiment on silica alone, we don't observe all these phenomena. We have not observed this phenomena. And, but here it shows that we have some negative signal, and maybe this polymer is located at the frontier between silica and metal.
I'm afraid we should move on, even though there are some more questions. Thank you very much.